lecture on Introduction to Coordinate Systems, which is a foundational part of GIS and something I'm really excited to introduce you to. And so to start, I have a question for you all. Which country is larger, do you think, Greenland or Africa? And so this is a view of the continents of a projection that we're very used to seeing on like the atlas or other flat maps. And so let's take a minute and think about which landmass is larger, Greenland or the continent of Africa, okay? And this website is really cool. It's a great hack if you want a table topic or icebreaker for your Thanksgiving dinners. And let me show you this website really quick. .com, and in the top left, you don't see it in the screen, but you could type in the continent or the country that we want to highlight and compare to other countries or land masses. So I typed in Greenland and there it is. It's highlighted. And now all you do is you click and drag it over the landmass that you'd like to compare. So let's see how Greenland compares to Africa. Whoa, mind blown, right? It is a fraction of the size of Africa in real life. But because we're so used to seeing it in this perspective because of Mercator projection, which you'll learn about later in this lecture, we think it's a lot bigger than it actually is, right? So it's really a portion of the size of Africa. And you could do this for any country. Let's check out China and see how that compares to Russia. Whoa. Right? So as they go up to the northern poles, they actually get distorted, which we're going to learn about. So the true size of these countries and these land masses are a lot different than what we think based on this one projection that we're used to seeing. And so that kind of sums up the idea that projections are really important, and they distort and they sacrifice other, whether it's area, angles, distances, they sacrifice other qualities in order to showcase something. Okay, so definitely bring this up at your next dinner table. It's called thetruesizeof.com. And I'll just go through the next couple slides. So we learned that Greenland is actually a lot smaller than we think, and that's because map projections are really important. So let's watch the beginning part of this short lecture so you just don't hear me lecture for the whole period, and then we'll continue learning about coordinate systems.
Maps. They are attempts at representing our countries and continents. To follow the Wikipedia definition, in cartography, a map projection is a way to flatten a globe's surface into a plane in order to make a map. But there's an issue. It's impossible to do it in a way that is 100% accurate, because we need to transform latitude and longitude lines from the globe into locations on a plane surface. A lot of times people use an orange peel to explain this issue. If you peel an orange, you can't flatten it out on a table without messing the peel up. And so all projections of a sphere on a plane necessarily distort the surface in some way and to some extent in order for all of it to be present. This is why we have a lot, and when I say a lot, I mean a lot of map projections. Just searching for this video, I found around 250, and they are virtually infinite because depending on the purpose of the map, some distortions are acceptable and others are not. Therefore, different map projections exist and are created in order to preserve some properties of the sphere-like body that is the Earth, at the expense of others being distorted. They can belong to 7 groups, but I'm going to try to not get too technical here, especially because I have very little idea about the technicalities and mostly go at it from a visual perspective. The most well-known map projection used in the majority of maps across the world is the Mercator projection, presented by Flemish geographer and cartographer Gerardus Mercator in 1569. It's pretty old, and its generalized use has to do with the date in which it was invented. These were the times of the European colonialism and maritime discoveries, and so this map focused on representing any constant course of constant bearing of a ship as a straight segment on the map. To put it simply, if in order to get from southern France to Canada, your ship had to just go forward and never turn, then the map would show a straight line between the two locations. And so this projection became the standard map for navigation. However, it has a big issue. The Mercator projection inflates the sizes of objects away from the equator. This inflation is very small near the equator, allowing countries and continents there to be represented very accurately, but becomes distorted, being too big as it moves towards the poles. In this GIF, yes, GIF, not GIF, we can see countries being reduced to their true size. The ones near the equator have little to no change, while the ones up north shrink a lot. Greenland appears to be the size of Africa, when in reality it is 14 times smaller. Madagascar looks the same size as the UK, when in fact it is twice its size. Alaska seems to be the same size as Brazil, when Brazil is 5 times bigger. Antarctica looks gigantic, when in reality it is reasonably small. It's just at the southern pole, and so is reachable on a globe from all surrounding areas depicted here on the southern part of the map. And so, in order to depict that reachability, the map must show it distorted like this. I made a video about this specific issue once regarding the true size of countries. Eventually, the Mercator projection has become a little less used, although I think it's still the one in the majority of maps, but a lot of them switched to better ones, which are more accurate. A good example, and one extremely used nowadays, is the Robinson projection, developed in 1987 and adopted by the US's National Geographic Society in 1988 as their official projection. Before that, they used the Van der Grinten projection, which reduced Mercator's distortion in the center by concentrating all of it in the poles, which were extremely distorted, representing the globe as a circle. The Robinson projection almost solves it entirely though, and is honestly my favorite one because of this. The distortion in size is basically non-existent, and only the actual poles are distorted, like we see with Antarctica, but something which I think is justified with the necessity of showing its accessibility from all areas of the southern hemisphere. An interesting aspect in the majority of these projections is that the distortion is usually horizontally symmetric from the equator line. I'm sure there's some mathematical reason behind that. The Behrman projection from 1910, for instance, shows a really weird looking Central America, South America, and Africa. They are way too disproportionately big when compared to North America, Europe, and most of Asia, but they are disproportionate in a symmetrical way. So now we've understood 3 things. 1, all maps are distorted because it's impossible to depict a globe on a flat surface. 2, the type of distortion the map has depends on what it was made for. The Mercator projection was made for ship traveling, and so it prioritizes that, the courses and directions, sacrificing object proportions in some parts of the map. And 3, other maps have since tried to correct those errors in distortion, either prioritizing other aspects or attempting to depict our continents in the most accurate way possible on a flat surface. This is why there are so many projections. These maps we've seen so far have been, however, pretty standard and straightforward, in the sense that they are the way we expect a map to look like. But what about all the other projections that look way different? Let's start with this one. This is the transverse Mercator. Essentially, it stems from the Mercator projection, but depicts it in a different shape/angle. Now, again, I'm totally ignorant regarding the math behind this, but it's in the math that the difference is, and that's something out of my area of expertise. But there is the obvious difference in the visual aspect. Here, the pole sizes are pretty much near perfection, but other areas suffer as a consequence. Southeast Asia is way too big, as is South America, but Antarctica is perfectly depicted. So if we were to use the 2 Mercator projections side by side, we would have an almost perfect depiction of our world. We also have examples of maps which didn't have to deal with Antarctica's problem because, well, when they were made, Antarctica hadn't been discovered yet. Lambert's conformal conic projection from 1772 is a good example of this, and it's actually extremely proportionate in pretty much every aspect, although it is missing the tips of South America, South Africa, Australia, and New Zealand entirely. This map projection is apparently still the basis for a lot of the aeronautical charts used by air pilots, because a straight line drawn on a Lambert conformal conic projection approximates a great circle route between 2 points for flight distances. What we therefore understand is that essentially when cartographers and geographers develop these map projections, they always come up with specific mathematical principles behind them, and these principles can still be used today even if the original map projection itself is not, because it became outdated. That's why the amount of map projections is virtually infinite, because we can always change something in a projections equation, even if a tiny detail, or come up with an entirely new projection. Another example of a perhaps outdated projection is the stereographic projection. All of these have really complicated and technical names that I don't understand either, so the best way to understand them is by seeing how they look. This one is also known as a planisphere projection, and it dates back to antiquity, having been used in some of ancient Greece and Rome's maps. Depicted on a circle, instead of being centered on the equator, it is centered on the North Pole, with an increased level of distortion as you move away from it. But the errors were excusable, because the point was to depict the northern hemisphere with a high level of accuracy. However, some more recent projections just wanted to depict all continents with a minimal error possible. An example of that is the ARRI minimum error projection, which pretty much took the globe, cut it in half, and put two circles side by side. Some follow the same trend and use two different surfaces put together, like Van Leeuwen's GC, which uses two triangles.
There, because I think we've gotten the general knowledge of projections and distortions and some background context, and we learned there is a bit of math behind it. But for this intro to GIS course, we are just going to cover the basics, and we will keep going. But if you want to watch the rest of the video, I will link it in the homepage, and please feel free. So distortions. As we know, all flat maps distort shape, area, direction, or length when displaying features of a three-dimensional object such as the Earth, because you're trying to put it on a 2D surface. And so interpreting Tissot's indicatrix, or Tissot indicatrix because it's French. As you learn how to interpret this indicatrix, consider how the circles change on an equal area and conformal map projection. So on an equal area map projection, the circles will be transformed into ellipses, which you saw in the last video, but the area of the ellipses will be the same as the area of the original circles. That means although they will change shape, they will not change in size. On a conformal map projection, the circles will continue to be perfect circles, but their size will vary over the map. So my question for you is, which map projection is best? As you can see, there's tons of map projections, and the answer is they're all correct and they're all wrong. That single idea is what professional GIS analysts use every day when selecting a coordinate system. It seems like there should be one correct map projection, but because the Earth is a three-dimensional curved surface and there's lumps and bumps to the surface, maps are flat, so creating a map always requires compromise. And as a result, every map projection introduces distortion. And the question is not whether distortion exists, but what is being distorted. Different projections preserve different properties. Some maintain accurate area, making them useful for comparing the size of countries or ecosystems, and some preserve shape, distance, or direction, which are better suited for navigation, engineering, or regional mapping. So since no single projection can preserve all of these properties simultaneously, there's no universally best projection. Instead, the best projection is the one that is most appropriate for your mapping purposes. What am I trying to show or measure for this map? So that's what GIS professionals have to ask themselves. And the answer to that question should guide the choice of projection. So let's look at some common distortions and see why each projection makes a different trade-off, and why understanding those trade-offs is essential in GIS. And so this graphic is nice because it shows the compromise. So like if you want to preserve area, you're going to have some distortions. Is area, and an example of this is the Mercator projection. And so like we saw at the very beginning of this lecture, Greenland is distorted. The area looks a lot larger than it actually is. And that's because it elongates those circles closer to the poles, because it wants to preserve the center of the equator area land masses. And another common distortion is shape. An example of this is the continents near the poles appear stretched east to west on the Mercator projection as well. So the shape of the features is stretched, compressed, and it allows other qualities like the distance and direction to be preserved. And then another distortion is distance. An example of this is the shortest route between New York and London appear curved on most world maps, right? But in reality, the true shortest path is along the curvature of Earth. And then the last distortion is direction. And so the compass direction may only be accurate from certain points or along specific lines. An example of this is on some projections, directions are only true from particular points or along certain lines, when in reality, that's not the case.